Okay, remember yesterday I mentioned that the energy contained in a wave, when you're looking at sort of wave as a light as a wave, is the amplitude. That was your brightness. Okay, so your brightness is linked to the energy in the wave. Then came along the idea that, wait a minute, light's doing some funky things that we don't understand. It's kind of acting like it's a thing, like a discrete thing, okay, that's flying through space. And you're like, well, how does that make sense? So, experimentation, lots of work and lots of thought experiments and things like that came up with this nice little idea that light can act as a quanta, okay, as a thing that can be absorbed in its entirety and also given out in its entirety as though it's like a little ball, all right? So when they decided that was, or when they figured out that was a thing, they turned around and said, okay, so what's the energy related to? How do we describe energy and intensity in that model? Okay, so in that model, intensity becomes lots of packets of light. That's more intense. Okay, but what's the energy of the individual packet? What's that tied to? And they came up with this lovely, funky little, I'm scrolling on the wrong thing there. Here it is. E equals hc on lambda, also E equals hf. So these two little relationships give you the energy of basically a light packet, which we call a photon. So when you hear the word photon, they're talking about light not as a wave. They're talking about light as an individual discrete packet of energy, okay? So how much energy does that packet contain? Well, what frequency? The higher the frequency, the more energy, okay? So individually, the more energy. But if you have lots of packets, that's your intensity. All of a sudden you go away from the idea of the amplitude and that kind of thing from the wave model version of what light might be.
So aren't the single packets still like
They,
I can know.
yeah, no, that's when you look at the double slit experiment, right? When you use the double slit experiment, you end up with something called interference, okay? And the interference is really a wave phenomena. So you'll see interference. We'll actually look at that properly. But when you're looking at light as a packet, what they're doing is they do a different experiment, okay? And in that experiment, they fire electrons, and the electrons moving through the double slit experiment, they exhibit wave properties. So they create interference patterns. The short end of that is that particles have a wave nature and light has a particle nature. So light going through the double slit experiment is showing that it's a wave. Okay, that's not the experiment you use to show light as a packet or as a photon. That's not what you do, all right? When you send electrons, a stream of electrons through the double slit, you see interference. You're like, whoa, the electrons are acting like waves. All right, so there's this weird duality that a guy called De Broglie figured out a long time ago and got a Nobel Prize for, that matter could pretend to be a wave, light can pretend to be a particle, okay? So that's part of the course, definitely, but it's not, what you mean is like that other version of it, okay? That's what you mean, and you'll see it all fits in when we get to the end. You'll see, oh, okay, that's how it all fits together, all right? But right now, if you imagine a photon as a little packet of energy that's discrete, okay, we always draw it like that because you're kind of implying that it has a frequency, has some wave nature part to it, right? And what we need to know about that is what's the frequency of that light. So the frequency of that light, if I want to know how much energy that photon contains, the energy is equal to Planck's constant multiplied by the frequency. And Planck's constant is a constant, it's just a number, all right, that is not important right now, okay? It's not really part of this chapter, but they've added it in here so that you start to get the feel that, yes, light can be a wave, but it can also act as a particle, all right? And so what's the energy of light? Well, as a wave, amplitude, that's brightness, okay, energy. Well, as a particle, frequency is where its energy is. Sorry?
Just like a lot of particles.
Yeah, it's like billions and billions of photons are acting like billions of particles, and it also leads to that other beautiful discovery that these photons have momentum. Okay, so we've all seen science fiction. My last backdrop on my screen was that film Passengers, right? And so, do you remember at the start of that film, if you ever saw it, it had a massive sail, and that's how it was accelerating across, the universe, and so, or the galaxy.
It's the solar window.
Yeah, I know. So that's right. So basically, yeah. Oh, but the solar wind is actual particles, whereas what we're saying is the light itself acts like a particle and can, when it hits a surface, it bounces off it. Basically, so there's a change in momentum. So basically, light itself exerts a force. All right. So lasers. Let's have a quick read about lasers. Let's see what they are. The first laser was invented in 1958. However, Einstein in 1970 predicted stimulated emissions. He was such a smart dude. Predicted lots of stuff that they found later. Okay, light emitted by a common lamp is incoherent. Now, these are the words that are important when you're trying to do questions, okay? So the light from a common lamp is incoherent. So it's lots and lots of different wavelengths. We know white light is just an amalgam of lots of different colors, the colors of the rainbow. Added together, you get white light, okay? That is many photons, many frequencies, and in many phases. So they're not in phase with each other. There's nothing, it's kind of dirty light, basically. It's everything everywhere, all right? Okay, then you move on, all right? So incoherent, all right. Even if the beam is filtered so that it is formed with a single frequency, in other words, you stick a red filter in front of your beam. Now, all the other light is absorbed and just the red gets through. Now you've got light that's kind of cleaner because it's just one frequency, it's red, okay? But again, it's still incoherent, all right? It's not collimated, it's incoherent, it's not in phase. So you've got lots of waves all over the place, all right? But they're all red, okay? They're all that frequency, all right? Now you take it further, and so you say a beam of photons having the same frequency, phase, and direction, all right? That is a beam that is of identical photons is said to be coherent. A beam of coherent light spreads and weakens very, very little, all right? So that's your lasers, okay? Now, a laser is a device that produces a beam of coherent light. The laser has a source of atoms called an active medium, all right? Which can be either a gas, liquid, or solid. The atoms are excited to metastable states. So again, these are the words when you hit that one-off multiple choice question where they throw the language in there and you've got to decide which option is correct. All right, that's the depth of what you need to know. Active medium, which can be either where was I? Metastable state, particularly excited state of an atom that has a longer lifetime than the ordinary excited states by an external source of energy. So here you see, when most of the atoms in the medium are excited, now that just means that the electrons in that material have all taken on energy from some external source, like pushing the button on a laser pointer. The battery operates, it energizes the medium. Okay, all right. So when most of the atoms in the medium are excited, a single photon from an atom that undergoes de-excitation can start a chain reaction. What that means is that when you provide energy to those atoms and those electrons jump up, what they do is they don't stay up for very long. If you imagine there are billions and billions of them, and they're all jumping up, but they only stay up there for a very, very short time. They jump back down again. When they jump back down again, the atom gives off a very specific amount of energy, okay? A very specific frequency when it jumps down. And so that specific frequency becomes the light. It comes out as light. That's where the light's coming from. The electron jumps up by taking energy in from the battery and then jumps back down and gives it off as a bit of light, okay? Now, what's funky about these is that they all start building on each other, All right, so one does it and then it stimulates another one to do it, which stimulates more to do it, and it ends up setting up sort of this cascade, all right, where light is just being all formed. They interact with each other, forcing each other to become coherent and all in the same phase, and they all start bouncing back and forth between these two mirrors that are inside. Now, one of the mirrors will have a little hole in it because at some point, now at the speed of light, all of this excitation is going like crazy. Enough light is going to get out of that little hole, which becomes your beam. So inside, it's all set up as all of these excitations are lining up and reinforcing each other. And then there's a certain proportion of it that gets out through the hole. All right? That's roughly how it works. And if you watch the video that I've attached to this bit, the guy will show you with pictures and little animations. They go, oh, okay, so that's what's happening. And he's got a piece of ruby and he illuminates it and it's ridiculously cool, okay? So, yeah. All right, LEDs. Again, there is another video. Basically, the characteristics of an LED, light-emitting diode. Firstly, a light-emitting diode has a symbol that we use, okay? The symbol for a light-emitting diode is this triangle with a line. Now, no one's ever told me this, but this is how I imagine what the symbol means. Okay, the symbol basically means to me... Yeah, I know, all right? I'm getting there. Getting there. All right, look. So this is a diode, and you connect it with, as in conventional current. So conventional current is going in this direction. What the diode will do is it will allow the current to flow through it. There'll be a tiny voltage drop that activates the diode because the current needs to overcome a sort of internal resistance in there, okay? And we'll talk about that in a second. And all of a sudden, it will flow. Now, if this is a light-emitting diode, then you add a couple of arrows that signify light coming off the actual component. If it's not a light-emitting diode, it's just a diode that they need to restrict to the direction of current for some component in something that they built, and it's in there, but it doesn't need to emit light. But we make light-emitting diodes specifically because they emit light, and they're really useful, okay? Now, I see this as the arrow in the direction that the diode allows the flow of current. Now, if you unplug it, turn it around, and plug it in the other way, then it's trying to send the current the other way. Now it goes reverse bias. The other way is forward bias, which is good. It lets the current through. Reverse bias puts up a wall. So the diode basically becomes infinity resistance, right? And stops the current from going through, okay? So it's like a gate that lets current go through in one direction only, all right? Okay, now, light-emitting diodes are diodes that emit light when a current passes through them at a suitable voltage, all right? So below the suitable voltage, nothing happens. After the suitable voltage, it switches on and will usually drop about 0.7 volts. If it's forward bias, you notice that you don't really get any current until you hit that switch on voltage and overcome that internal resistance, and bang, it becomes a gate, and all of a sudden, all of it goes through, okay? You've lost a tiny bit of voltage at start, depending on what it is. You're right, it's different, depending on which diode it is, but you just know there's always a little bit that's in there, okay, that is kind of used up getting through. And it allows this is current, voltage, okay? At this voltage, now the current goes up and the voltage only very slightly increases. Now, flip the diode around and put the current the other way, all of a sudden, notice to explain what this is you're increasing the voltage, but look at how much current you're getting. You're getting a little bit of current leakage in there, but you're not really getting, there's a lot of resistance to it if you reverse biased it, okay? And then all of a sudden, right here, you've gone to a certain voltage where you've killed the diode and it is now broken, all right? So you burn out the diode when you go too far with the voltage, and then it just opens up and becomes a piece of wire and just lets it all through, Okay? So that's what...
Why is it negative?
Oh, because the direction of the current. Yeah, the direction of the current. So if it's forward biased, it's, and then that's going the other way, all right? So that's basically the operation of the diode, all right? Now, sometimes be very careful. Sometimes the scale, you never see graphs where the scale's different on one side to the other, but sometimes I have seen in the past questions where the scale here is, there's 0.7 over here, right? But then over here, the scale is like, to be able to show the breakdown, and the scale is like completely different on this side, which is confusing if you're not like ready for that, okay? So just making sure you're expecting that sometimes the scale on this side is like ridiculous because you've got to get to that voltage to show that part of the graph where it breaks down, and it's like out here somewhere. If this is 0.7, that breakdown is over here somewhere and it wouldn't fit on the graph. So they changed the scale to fit it on so you can see it. All right? Okay, so now this is the part that's, okay, kind of what happens. And again, there's a video that explains what's going on inside the material. Basically, you have here, so LEDs use a PN junction. It's a positive, negative junction. Okay, so there's a material that is a charge, known as charge, it's got charge carriers, okay? So it's sort of the positive end of the material, and then your negative end has the N type, which is your electrons that will do the work of moving along, all right? So, okay, LEDs use a PN junction to create these specific conditions. This is where a P-type semiconductor, which contains free positively charged carriers, known as holes, in other words, valence electrons. That's what it is. It's places for the electrons to go. So, yeah. So what happens is this is ready to receive, and it's fine if it's just sitting there. You've just attached it to a material that has lots of electrons, and naturally, some of those electrons will jump across, okay? And you'll end up with like a little happy space in here where they're all together and then they stop moving, all right? So this is just the diode that's not plugged into anything, all right? You end up with this depletion region, but there's not enough energy in the electrons over here to keep on pushing. So what do is you connect it and you put more electrons in one end. Put more electrons in one end, and all of a sudden now there's an abundance of electrons, and there's enough sort of energy to start pushing past this band gap, and you end up with the holes moving this way and the electrons moving that way, and you end up with forward bias, and now there's a flow. Okay? Now, yeah, that's like, oh, well, why bother? Couldn't you just put a wire in there and it will let it flow? You don't need to worry about this. Well, the point is that if you've got a component, an electronic circuit where the current can go both ways and you need it to just go in one direction, what will happen is this diode will only let the flow go in that direction. It works nicely. If you take the diode and flip it around, well, now you actually expand that region in the middle, and it just becomes infinitely resisting. You get infinite resistance there. All right. And again, do you want to watch the videos? Okay, because the videos will then show it with proper animations. Okay, so if you're watching this at home, watch the videos now. We'll just have a very quick look. I just want to make sure that you've seen the animations now. Okay, so we've seen both animations of forward and reverse bias. Okay, at that part, so you could visualize it a lot better than I can explain. And now you've got your notes as well. All right, so you can see that as the electrons move over into the holes, they are occupying lower energy levels, which means they've got too much energy as provided by the power source, and then the excess energy comes off as photons of light. Now, those photons of light are specific. They have specific wavelengths. That's why a red laser isn't filtered into red. It is red. So you probably know that already. But So a blue laser is actually making blue light. A red laser is making red light. Okay, so all those different colors, they're just using different materials that give you specific energies of those photons that are coming off, all right? No, they're not. They are actually, the red LEDs are making red light. And that's why they're really good. And now, obviously, you might be thinking, wait a minute, we use like LEDs. Now, if anyone knows more about this bit than I do know to make white light, like most of my light globes at home are LED light globes now, and they're white. But we know white isn't one color. White is lots of colors. So my understanding was that they'd basically found versions of blue that are almost white, and really, you're really looking at a blue light. But
It's like
engineers are very tricky, and they work things out. So, yeah?
it's a blue diode, and it's lost for like the
Okay, so that's what they're doing. All right, so they're taking the blue light, and then they're altering it on the way out to make it appear white, basically.
basically doesn't represent.
Like the same as the fluoro tubes. Yes, that's right. Yes, cool. That makes sense. That's good. All right, so inside this lamp, you've got mercury vapor. It's only one kind of atom. Now, did you ever wonder how did they know that the sun's made of hydrogen and how that the universe has what elements are out there? Well, if you take the elements, expose them to some energy and get the spectra of light that comes off those elements, they all have their own fingerprint. Okay, so every element has its own set of photons or light that comes off them when you energize them, right? And so mercury has its own specific set, right? So we know it's mercury because in the lab, you look at mercury, you look at what wavelengths come specifically off mercury, and you go, now when I look into space and go, oh, I see those same exact peaks coming from that part over there. I know there's mercury up there, okay? Hydrogen does it, they all do it, okay? So that way you just analyze the light coming in from space and you know exactly what's out there without having to actually go and take a sample, right? It's very cool, right? And when you look at that, what you're really looking at is very specific energy levels. Come on, stop. Very specific energy levels from the electrons, from the specific electron arrangement of mercury atoms that does this. They are jumping up and down and giving off photons of light at very specific frequencies. And so you know it's mercury, wherever it is, because all mercury will be the same in the universe. All right? So that's really cool, right?
So the direction is like, we get the helium in, but then it's moving.
Yeah, and then it's moving. You're like, what's going on? Exactly, exactly. Now, one last thing before hopefully the bell goes, is the synchrotron. Synchrotron radiation. Again, there's another video, but I'll just be very, very quick with this, and the video is pretty good. The video details synchrotron light. So the synchrotron, do you know we have a synchrotron in Victoria? We have one out in Clayton. It's this big round building, okay? So what they do in there is that's a big science building, lots of experiments, all right? So what they do is they take a electron generator, basically a piece of metal that you heat up and electrons will jump off it. And then using very powerful magnets, they take those bunches of electrons and shoot them down a steel tube that is evacuated. There's less inside the steel tube than there is in space. Okay, so this tube has a complete, almost perfect vacuum in it, so that it doesn't interfere with the electrons as they're trying to move through. So down the middle of that tube, magnets on the outside are manipulating those electrons so that they accelerate them, but then they keep bending them to go around in a really big loop. All right. So these are the electrons moving. Now, the point of it is that what it does is it makes it a very brilliant, a very powerful light source. How does it make it a light source? Well, you take those electrons, and as they bend, as the magnets bend their direction, as they go around this huge ring, which is like couple of 100 meters in diameter, right? It's a very expensive toy, basically, this thing. As the electrons move and they change direction. When they change direction, basically they lose energy in that change of direction and they give off light. And so you can see that's what they're showing here. As the electron's been bent by the bending magnets, light will come off and it will travel down another tube, which is there, and that tube takes it down to a laboratory. And you can then filter and aim that light at whatever experiment you want to do. So in other words, if you need to know the arrangement of atoms in a particular material, you shine specific wavelengths at that material and it'll create a scatter pattern. Electron flow is that way, current flow is that way.
Yeah, it would.
Yeah, so not a good diagram. You're right, well done. That's good. That's good. All right.